Hello and welcome back to the course on machine learning. In the previous tutorials, we learned quite a lot about the k-means algorithm. We talked about how it works in the background. We actually performed a manual k-means algorithm, which was lots of fun. Then we talked about the random initialization trap and what the k-means plus plus is. And in all those scenarios, we kind of worked with a predetermined number of clusters, whether it was 2 clusters or 3 clusters. And we talked about somehow finding out the correct number of clusters for a given data science problem. In today's tutorial, we're actually going to talk about the algorithm behind finding out the right number of clusters. So we'll learn how to decide what number of clusters to input into your k-means algorithm. So let's get straight into it. Here we've got a challenge or a data science problem. Again, we've got only 2 variables, the x and y coordinates. Just for simplicity's sake, in reality, it can be any number of columns or variables. And here we've got the scatter plot representing our data set. Now, if we run the k-means clustering algorithm on this data set with 3 clusters or with k predetermined to be 3, then the result will look something like this. And not just something like this, but exactly like this. We've got the 3 clusters that have been identified, and we already know that we would need to run the k-means plus plus algorithm just to avoid the random initialization trap. But again, for simplicity's sake, we're just going to call it the k-means algorithm. So we've got the 3 clusters. Now, in order to understand if, for instance, 2 clusters would have been better in this scenario, or maybe 10 clusters would have been better, we need a certain metric. We need a way to understand or evaluate how a certain number of clusters performs compared to a different number of clusters, and preferably that metric should be quantifiable. So what kind of metric can we impose upon our clustering algorithm that will tell us something about the final result? And there is such a metric. It's called the within cluster sum of squares, hence the WCSS on the left. And that is the formula, how it's calculated. This is an example for 3 clusters. Now, at first glance, this formula might look a bit overwhelming or complex, but in reality, it's super simple. So in line with our mission, making the complex simple, let's break it all down. What is going on here? Well, we've got the 3 elements and each sum, so this symbol stands for sum. Each sum is calculated for each cluster. In fact, it's calculated within that cluster, hence the W at the start. So let's look at one of them. Let's look at the center one, for instance. Here we're taking every point inside cluster 2. And that's exactly what is written out here. And this is, believe it or not, a valid way to write this sum. So you just write the P with the index I is inside cluster 2. And we're going to take a sum across those points. And what we're summing is the distance between each point inside cluster 2 and the centroid of cluster 2. And then we're squaring that distance. So we're taking the sum of those squared distances. So now if we have a look at our chart, I'm going to keep the WCSS on the left. So for instance, for cluster 2, there it is. We're taking the centroid and we're calculating the distance to every single point. So to that point, then we're squaring it. To that point, then we're squaring it. To that point, then we're squaring it. To that point, we're squaring it, and so on. So we're taking the square, the sum of all the squares of all these distances, and we're summing it. And then we're doing that. So we're doing that for the first cluster, we're doing that for the second cluster, and we're doing that for the third cluster as well. And so as a result, we get this total sum, so the full sum, and that is going to be our metric. And actually, it's quite a good metric in terms of understanding or comparing the goodness of fit between 2 different k-means clusterings. And how do we know that? Well, let's have a look. Let's rewind back to when we had 1 cluster. Let's see how that metric, WCSS, is going to change as we increase the number of clusters. All right, so there is our chart with just the 1 cluster. As you can see, that is our centroid. And for every single point, we have to measure the distance between that point and the centroid. Then we have to square that distance, and then we'll have to add all those distances up. As you can see, we'll get quite a large value because this centroid is quite moved away from all of the points. They all have to reach towards it. So let's just visually remember what this looks like. And That will help us kind of remember what that distance is, not in terms of the absolute value, but just what it feels like. It's quite a large distance right now. So I'm going to increase the number of clusters to 2, and let's see how everything changes. So there we go, that's 2 clusters, and as you can see, now instead of having 1 centroid in the middle, we have 2 centroids. So each one of these points no longer has to reach all the way to the middle, or the distance isn't that great. All you have to do is just calculate the distance to this centroid. As you can see, it's less. And then for these centroids, for all of them here as well, the distance to this centroid is less. They don't have to reach all the way to the middle when you're calculating that distance. So there we go. That means that the total distance, or the total WCSS that we see here, is going to be less than when we had 1 centroid. Now, once again, we're going to increase the number of clusters, this time to 3. So just remember visually what 2 clusters looks like, and then we'll compare to the next image. So there we go. Now we have 3 clusters, and as you can see, nothing changed in cluster 1. So this sum is going to be the same. These 2 sums have changed. So now instead of 1 cluster, these 2 groups of points are recognized as separate clusters, and therefore they have their own centroids, and the distance has again decreased, because you can see now all of these points are closer to their own centroid than they were to the centroid which was in the middle, and again these points are closer to this centroid overall than they were to the centroid here in the middle. So therefore, as you can see, the WCSS distance is decreasing. And what is the limit of that? How far will it keep decreasing? Well, let's think about it. Let's say we increase the number of clusters to 4, 5, 6, and so on. How many clusters maximum can we have? Well, we can have as many clusters as there are points or elements in our data set. So as many points as we see on our chart, that's how many clusters we can have. So if we have 50 points, we can have up to 50 clusters. Because after you go over 50, or after you go over the number of points, there's no more points to actually cluster. Every single point has its own cluster. So, and in that case, what will the WCSS equate to? I'll give you a second. If you want to, you can pause this video just to think about that for a second. If we've reached the number of clusters equivalent to the number of points in our chart, or the number of, which is the same thing as the number of elements in our data set, then what does WCSS equate to? And exactly right, the WCSS will equate to 0, because every single point has its own cluster, and therefore it has its own centroid, and that centroid is going to be exactly where that point is, and therefore the distance between the point and the centroid is going to be 0. If you square that, it's going to be 0, and if you add up all those squares, it's still going to be 0. So as we can see, the WCSS will decrease from a substantial value when we have 1 cluster all the way down to 0 as we increase the number of clusters. So it is a good metric, but at the same time, it's constantly decreasing, right? So it's constantly getting better and better and better. And that's because, as you can see, the less the WCSS, or the higher the number of clusters, the better the goodness of fit. We're fitting our data better and better and better, and therefore the lesser the WCSS, the better the goodness of fit is deemed to be. But how do we find the optimal goodness of fit? Yes, it keeps getting better, but is there a sacrifice that comes with that improvement? And that is exactly the case. Let's have a look at this visual chart. This chart represents how the WCSS changes as we increase the number of clusters. And as you can see at the start, the WCSS starts at quite a large number. It doesn't really matter what this number is measured in, what the absolute value is, and things like that. What matters is how it changes. So the relative comparison between different k-means clustering methods with the different number of clusters. So you can see here that it jumped from 8,000 down to 3,000. That's a massive change of 5,000. Let's just call them units, 5,000 units. And then from 3,000, as we increase the number of clusters from 2 to 3, it jumped from 3,000 to 1,000. Again, quite a large drop. And then from 3 to 4, what's going to happen is going to jump from 1,000 to maybe 800, then from 800 to 600, 600 to 500, and so on. So as you can see, the first 2 improvements, or first 2 changes from 1 cluster to 2, from 2 to 3, created some huge jumps or huge drops in the WCSS. Going forward, the WCSS drops not as substantially. And this is our hint at selecting the optimal number of clusters. And the method we're going to use is the elbow method, and it is actually very visual. All you have to do is look at your chart and look for that change, or that kind of like, it does look like an elbow. Look for that elbow in your chart where the drop goes from being quite substantial to being not as substantial, the improvement is not as great. And therefore that point in your chart is going to be the optimal number of clusters. In this case, it is indeed 3 clusters that is the optimal number. And as you can imagine, this method is quite arbitrary. So sometimes the situations are not as obvious. Sometimes the elbow might not be as evident as in this case, and therefore somebody might pick one number of clusters, someone else might come along and pick another number of clusters. But that is a judgment call that you need to make as a data scientist. Sometimes you need to decide on how your analysis is going to be structured, and this is one of those cases because you are deciding what type of k-means clustering algorithm to run. You're inputting that value of k, and yes, it can be arbitrary, but if you're not really sure, then you just need to kind of run the k-means, for instance, with 3, look at it with 4, look at it with 2, and like see what the difference is and make that judgment call on which k you think is optimal for your analysis. Because ultimately you are the person creating this analysis, and you need to decide which number of clusters is optimal. So the elbow method is just an approach that can help you make that decision, but at the end of the day, it is your decision. So there we go. Hopefully you enjoyed this tutorial, and now your arsenal of k-means clustering is quite broad. You have quite a few tools in there, and I can't wait for you to jump into the practical application of this method. Adeline has prepared some very interesting code challenges for you, and you'll be working with this method both in R and Python. It's going to be very exciting. So good luck with that. I'll see you next time, and until then, enjoy machine learning.